Hello, this is Peter and we're here for part 2. We'll do a quick review of the part 1 results. I added a few things. This, to remind you, is a half model of a board bolted to a pipe at 3 spots and the pipe supported on a revolute joint at the bottom, and these 2 holes represent where an arm supports the rotation. So we're going to look at the stress in detail around this point, but let's briefly look at the forces going through the joints that hold the board to the pipe. So those are fixed joints, and we can see there's a force that is largely in this direction. The next one has one more in the opposite direction with the big up component, and then the third one has this direction. The revolute joint has a total force of 392 newtons, and the force reaction preventing rotation around that joint is 272 newtons. So those are all the forces acting, and these forces are all very accurate. What's less accurate is the stress in the part around this hole, and that's because a fixed joint is not an accurate representation of a bolt shaft in a hole, because the bending of this and the force would cause the bolt to push on one side of the hole, and the stress will be quite different. So this stress is artificially high, and in this video we're going to take the values of 66, 282, which are the 2 in-plane forces, the pull-out forces. We won't be using the normal force because the stress in the part is largely due to the shear and not so much, that's just preventing the board from passing through the pipe. The thing we're going to do is take our model, which we had the mid-surface model, and I showed how I kept only mid-surfaces and removed half the model. This is a copy of that for a submodel, and if I hide all suppressed, there's just a single solid with the hole of interest, and we're going to bring this geometry into a new workbench. We're going to bring out a static structural. We want the same engineering data to be available, but we're bringing in different geometry, so we will import the geometry that's open, the solid submodel geometry, and quickly build a model of that. What I've typically done in these models is create fixed joints, fixed supports where I have cut the board. So my normal workflow would be to pick these 2 faces and just have them be fixed supports, fixed, and the more realistic method of loading this hole is to insert a bearing force, and that bearing load can be done in components. Those components can be in that coordinate system, which I'll create now. It's in the other model, but it's not in this one yet. So if I pick that face and insert a coordinate system and then orient the x-axis, the z-axis to be normal to some geometry, like this face here, we now have the same coordinate frame, except I need to flip z, and then X is toward the inside and Y is up, and that matches this joint coordinate frame where X is inboard and Y is up. So I can directly copy these values of X and Y, 66 and 282.6, and insert them in this bearing load, which will be in that local coordinate system of minus 66 and minus 282. So there's the two shear forces, and now we'll just do a little meshing. The meshing will be aided by a method on this body of sweep. So we will sweep that with a source face being this face here, and we want 4 elements through the thickness. And on the mesh, well, we're going to inflate this method and use the edge here as the place to define, say, a total thickness of 5 millimeters to put 5 elements in, and we're going to use an overall element size of 5 millimeters and put some edges, insert some sizing on that edge and put like 20 elements around it and see how that looks. So what we see is a very nice high stress on the side of the hole where the bolt is pushing, and a very low stress on the side of the hole the clearance would accumulate. So this is a far more accurate representation of the stress around that hole, and it's much lower than the 171 megapascals we saw, even though the same amount of force is going through that material. So that is what I wanted to cover. There is one alternative little bit of method that I haven't used before, but I've read about it, and I will show you that quickly, but I found it was not helpful in this case, and that's to go back here and take the solution from the system model of mid-surfaces and use that to set up something here, which we will refresh, and it shows up as a submodel. And in the submodel, we can use the cut boundary constraints, and it can go and use the displacement results on these two faces, this face and this face. It can select those and import them and apply those in place of the fixed support, which I'll suppress. So this is called the submodeling method, where the displacements from the system model are included in this. And let's solve that and see if it's helpful. The same bearing load is still over here, but you'll see what I mean when you get the results here, that it wasn't that helpful. And here we have an enormous stress concentration up on the boundary. So I guess there is one setting I forgot to do here, which was the transfer was shell to solid, but even with that, I get the same basic result. Just go ahead and solve again. And that helped a little, but 5,000 instead of 19, not what I was expecting. So I was expecting the high stress down here, and it's up on the boundary. Anyone who knows a lot more about submodeling, this was my first test of it, and I'm finding not helpful in this case. So my standard method of fixed support with a long way from the area of interest still seems like the good way to go. So leave a comment below if you have some ideas about this submodeling or any other questions. Thanks for watching.